This is PHYZ the universal, and today I'll be teaching you the way you can derive Newton's second law of motion. This is the formula I'm talking about, and this formula relates the mass and the acceleration with the force. Or in other way, you can say a force applied to a unit mass of 1 kilogram produce an acceleration of 1 meter per second per second. Well, this formula may look way more weird, but in the normal sense, this formula is very important in many fields of science, from aerospace technology and rocket propulsion technology. Well, this formula rates two vector quantities. There are two vector quantities. We have the force being the vector and the acceleration be a vector quantity. By the way, what is the vector quantity and what is a scalar quantity? Well, the vector quantity, these are quantities with both magnitude and the direction, whereas the scalar quantities, these are quantities with only the magnitude. Example of the vector quantity is just the force, and the scalar quantity is just the mass, speed, and many other quantities that you know. So in this derivation, I'm going to assume that there is a constant force being acted on an object. Why am I saying the constant force? Because in many other fields, well, this force might not be constant, like in the rocket propulsion. As the rocket ascends in the air or in the space, its mass gradually decreases rather. So basically, the force will be altered according to the decrease in mass of that rocket. Well, there are more mathematics added in this formula, but in this level I'm going to teach you how can you derive this formula. Assume that there is a constant force being acted on that body. Great. So before we get our tutorial started, I'd like you to be familiar with the following terms. What it means by the term momentum. Well, in many textbooks, momentum is defined as the product of the mass of the body and its velocity. And momentum is given by the small letter p, and it's given by the product of the mass and its velocity. Now assume that we have a body of mass 0.4 kilograms and it's moving at a speed of 100 meters per second. What do you think would be its momentum? So its momentum will be 0.4 kilograms multiplied by 100 meters per second, which is basically 40 kilograms meters per second. So this is the momentum of that body moving at a speed of 100 meters per second. The other term that you have to be familiar with is 1 Newton. 1 Newton, this is the force which acts on a unit mass of 1 kilogram and produces an acceleration of 1 meter per second or 1 meter per second squared. So basically 1 Newton equals to 1 kilogram meters per second squared. So this is what it means by 1 Newton, and keep in mind that this SI unit is going to be used in the later stage, since I'm going to go over some few problems related to this formula. So you guys stay tuned to this tutorial. Great. Well, having seen these fun terms, and now we can go ahead and look at the way we can derive this formula. Now assume you have a body of mass m, and it's on the ground, on the level ground, and it's moving with its initial velocity u, and then after time t it is acted upon by an external force F. This external force lasts for time t, and this force caused this body to accelerate to its final velocity v. So just to recapitulate what I just said, assume that you have a body with mass m, and it has its initial velocity u, and it is being acted upon by an external force F for a certain time t, which causes that body to accelerate to a velocity, to its final velocity v. So what would be its initial momentum? The body's initial momentum will be mu, and the body's final momentum will be mv. So this is initial momentum and this is final momentum. Right. Having seen its initial momentum and its final momentum, we can go ahead and look at the way we can derive. Actually, I shouldn't have drawn this way. Let's see, touch on the ground. This is the same body. So as you can see, there are more than one effects of force. When a force acts on an object, there are many effects that can happen, but in this case I'm going to show you two effects. When a force acts on the body, example this body which we have just demonstrated, this body may speed up or may slow down, but in this case you can see the body actually accelerates. What is the force cause the body to accelerate? So basically the acceleration produced when a force F applied to this mass is given by the final velocity minus the initial velocity divided by time. Right. The initial momentum of this body is given by the product of its mass and its initial velocity, whereas its final momentum is given by the product of its mass and its final velocity. I think at this point we are together. So according to Newton's second law of motion, the force applied to an object is direct proportion to the rate of change of momentum. And by the way, when you say the rate of change of something, that means you take a quantity, you divide by the time. So according to Newton's second law of motion, a force is direct proportion to the rate of change of momentum. Right. So we can go ahead and expand this formula. So the force is direct proportion to the rate of change of momentum. So you take the final momentum, you subtract the initial momentum, then you divide by time. Right. So in this case, let's just move this concept of proportionality, but I'm going to show you the way it is removed. I'm going to assume that the force is basically the final momentum minus the initial momentum over time. Great. So let's move this. So at this in there, so we can go ahead and proceed. So basically expand this formula as F being equal to the other side, F being, let's factor out mass, so this is the simplified version of this equation. So as you can see, the terms inside is the final velocity minus the initial velocity over time. And if you can recall from the introduction, the final velocity minus the initial velocity over time, this term represents the acceleration. So basically we can go ahead and write this formula as F equals to ma. So this is the formula I was talking about in the first time. So here it's the way you can drive this formula, and just pretty simple as long as you combine with your mathematics skills and physics skills. And I'd like to warn you that here we are showing that a constant force is being acted on that object. It's not, the force is not variable, it is constant. So I can just make it clear. For the variable force, you need more mathematics to go to the part of derivative and and integral. So we're not going to go over those advanced concepts of mathematics, but now let's keep the things simple so that we just understand it. As I promised you, you know that this is the rate of change in momentum, so this can be written as F is direct proportion to the rate of change in momentum, although it is simplified. So why there is no constant, we have to ask ourselves, we can't see any constant here, but let me show you the way you can just remove this constant of proportionality, and why there are no constants here, like maybe like F is equal to 2 ma well, like Newton's Newton's law of universal gravity, which is F is equal to G m1 m2 divided by r squared. This is the constant, but in this formula we can't see this constant. So where is that going? Let me show you how this constant disappeared and why there is no constant. The constant is the actual one, but how did it come to be one? So this is what I'm going to show you right now. So we know that F is that proportion to mass multiplied by the acceleration. Now let's assume that we have a unit force. Let's go to 1 Newton, and we have the mass of 1 kilogram, and we have the acceleration of 1 meter per second squared. This is basically what it means by 1 Newton. Great. So in order to move this constant of proportionality, we need to replace this symbol with a certain constant, and I'm going to assume that I'm going to use K. So F equals to K multiplied by M multiplied by A. Now let's make K the subject. Making K the subject, we end up with K being equal to force divided by mass into the acceleration. So let's plug in these values that we have for the force, mass, and the acceleration. So we have a force of 1 Newton, and we have a unit mass and the unit acceleration. So basically we have 1 here. So we're going to take 1 divided by 1 times 1. This is basically 1. So going back to our formula, let's use this. We have force equal to KMA. So we see that the value of K is definitely 1. So F equals to MA, since 1 multiplied by MA is basically MA. So that's why we write this formula as mass, F equal to mass times acceleration. Pretty simple. I think here everything is clear. So now we can go over to the real life application of this formula, and we're going to go over some 2 problems before we close our tutorial today. And I think to be good if we can do it faster. So now let's assume that we have a tennis ball, maybe I'm not going to say a tennis ball, maybe a bicycle of mass 8 kilograms, and is acted upon by, well, external force. And let's assume that this bicycle is moving at its initial velocity of 20 meters per second, and when the force acts on that bicycle for 10 seconds, its final velocity becomes 80 meters per second. So what would be the force which caused this change in velocity? Alright, now using our formula which we've seen here, which we just basically derived, we see that F equals to mass times the acceleration. But looking at the data we have, there is no way we can have the acceleration, the value of the acceleration we don't have, but we can manipulate this formula and find the acceleration, and finally get the force needed to accelerate the bicycle of mass 8 kilograms from 20 meters per second to 80 meters per second. So let's expand this formula. We know that F equals to mass multiplied by the acceleration, but we know the acceleration is given by the final velocity minus the initial velocity over time. So let's put the big blocks here. So we know the final velocity minus the initial velocity over time. So up to this point, this formula is way more simplified. Now we can plug in the values that we have and proceed with finding the force needed to accelerate this bicycle. So basically, the mass of this body is 8 kilograms, and I'm going to intentionally put the units so that I can show you what it means by 1 newton. The final velocity is 80 minus 20 over 10. This is basically meters per second squared. So by simplifying everything in these brackets, we end up with 48 kilograms meters per second squared. But this may look way against the laws of physics and the SI unit of force, but there is nothing wrong about kilogram meters per second squared, since the definition of 1 newton is that 1 newton, this is the force which acts on a unit mass of 1 kilogram and cause that body to accelerate with the acceleration of 1 meter per second squared. So we can replace this SI unit, this unit, with the newton. So this is basically 48 newtons. Pretty simple. So this is the way the force can cause things to accelerate. So the next problem will be on the force causing the body to get to a complete halt or to a complete stop. Let's get rid of everything here. So now let's assume that a certain body of mass, let's say the car of mass 2500 kilograms is being acted upon by the external force and cause this car to get to a complete stop in 10 seconds. Well, let's say 30 seconds. Right. So we have a force of a certain magnitude of which we don't know, and it is being acted on that car and cause that car to decelerate or retard to its final velocity being equal to 0. That means it basically stopped. And then we need to find the momentum of the car, and you need to find the force which caused that car to retard or to stop in time 30 seconds. So what will be its momentum? Since this car went to a complete stop, then we know that its final velocity is 0. And let's say that its initial velocity u was 60 meters per second. So what would be its momentum? Its momentum is represented by a small p, which is equal to the mass of that car multiplied by its velocity. So the mass of this car is 2500. You multiply by its velocity 60 meters per second. So we end up with its momentum being 150,000 kilograms meters per second. Don't forget the SI units, because SI units in physics are very important. Great. So this is its momentum. So in the second problem, in the second part, we need to find the force which caused this body to retard. So the force which caused this body to retard is given by the formula which we have just derived right now. The product of mass and its velocity. I just write it somewhere. Seen by the product of mass and its acceleration. Right. So we can go ahead and expand this formula. Take the mass, you multiply by this expansion v minus u over t. We just close the brackets. So we can actually go ahead and expand a little bit more, and v minus mu over time. According to our problem, the initial momentum of this car is known, since the initial velocity of this car is known. But it turns out that the final momentum of this car is definitely zero, since the final velocity of this car is zero. That means it went to a complete stop. So the force required will be its final momentum being zero minus the mass of this car is 2,500 multiplied by its initial velocity of 60 meters per second, and then we divide by the time it took for the force to get this car to a complete stop, which is basically 30 seconds. So by calculating these values, we end up with the force being negative 5,000 newtons, or you can say it is negative 5 kilonewtons. Why is it negative? This force is negative because it is actually opposing the motion. It is going against the motion of this car. That means when the car is moving to the right, this force is assumed to go to this direction, to the left. That means the car would be seen to go into the left direction. That's why we have the negative sign on the force. Right, so this is the problem which lets the force causing the body to decelerate or to go to a complete stop. And now let's look at the way this formula is used in rocket propulsion technology. I'm going to have a simple problem. It's not going to be a bit huge. Now let's assume that we have a rocket here. I don't know how to draw the rocket, but I will try my level best. Maybe NASA. Well, these are nozzles. It have its streamline shape like this, and then there is some gases being expelled from these nozzles, right? and then it is moving forward in the space. Let's assume that these gases are expelled at the rate of 250 kilograms per second, right? And let's say the rocket initially has the velocity of maybe at the velocity of initial velocity of maybe 20 meters per second, right? And then we need, well, no, let's not assume that this rocket had the initial velocity of 20. Let's say it moved from the rest or from the launching pad with the initial velocity being 0, and then when a certain force of a certain magnitude, this is the rate of expulsion of the gases, emission of gases from these nozzles. Let's say initial the rocket was on its launching pad, and then when a force of a certain magnitude acted on this rocket, the rocket gains final velocity maybe of, let's say, 25 meters per second. So what would be this force which accelerates this rocket to the space? Now let's assume this is the constant force rather, and then after some time it's gonna change because the gas from these nozzles are causing the mass of this rocket to decrease every time as it ascends to the space. So basically we have this force. Let's apply the equation that we have just derived, since I've told you that one of the application of this formula is in the rocket propulsion technology. So F is basically mass times the acceleration, and then look at this term. Oh, these are these numbers, not the term. So the gas from the nozzles is expelled at the rate of 250 kilograms every second. That means every second 250 kilograms of gases are expelled from the rocket tank. And then I don't know, basically there's the mix of oxygen and hydrogen in the combustion chamber of this rocket. So let's rearrange this formula or expand it. So we have the mass, acceleration inside, then over time. So we have to manipulate this formula so that we can fit this value in. So we basically say mass over t, then you multiply by the acceleration v minus u over time. So you can see that the SI unit of this term which we have just created here is in this mass is in kilograms and the time is in second. So you see that we can just fit in this value over here. We have kilogram and then we have seconds here, so we can definitely fit this value. So we have kilogram over second, which is the rate of the gas, well, when the rate at which the gas is emitted from the nozzle of this rocket. And every time you have to be careful with these type of questions, because they're always very tricky and you need to play along with this type of equation and the way you can manipulate them. So we can just plug in the values that we have. So we have 250, and then I've forgotten something. Maybe let's say this was hacked. No, there's no way you can just put the time. No, there's no problem, because we have the rate of emission of these gases. So we can multiply by the acceleration. Well, not the acceleration. We have the final velocity being 25 minus the initial velocity. The initial velocity u, which is definitely 0, because this focus starts from rest. Alright, and then remember, I have not put the time because this is the rate of emission of gases. So this is in kilogram per second, so there's no need of putting the time here. So we take 25 in order to simplify this problem. So we have 250 multiplied by 25, and then at the end we're going to have Newton. We can go ahead and use the calculator to compute this value. By 25 multiplied by 25 is 625. Then you had this 0. So this is the force needed to accelerate this rocket from its launching pad to a velocity of 25 meters per second when the rate of emission of gases is 250 kilograms every second. So that's the way you can derive this equation, and these are very important real life applications of this formula. So for more tutorials in PHYZ and VESO, please advise you to hit the subscribe button for more tutorials that I'll be creating every week, so that you can enjoy good stuff from science, and especially in the derivation of different formulas. So you can go ahead and look at links which I've just put in the description below. The links of different videos that I made for some times ago, so you can go check them out, so that you can actually explore the world, because I believe we study science in order to explore the world, and we find out laws that govern the nature. So having said so, remember to share this video to your colleagues, your friends, and explore the world. That's the purpose I think we study science for. And having said so, I'd like to wish you a very nice morning and a prosperous life. Thank you very much.